Chapter 2, the two-body system. In the previous video, we explored the foundation of my hypothesis, how mass influences the space around it, and a possible quantum explanation of why. In this video, I'll go deeper and explore the two-body system. Okay, so we have established that mass will stretch space-time, changing the gravitational density around it. Let's try and picture what the gravitational density would look like. The gravitational density caused by mass will be even from all directions. If we look at our drawing, we see that the density on the left side of the mass will equal the density from the right side. Okay, you have to assume the drawings are perfectly even. I'm too lazy to actually make new ones, but don't worry, I have a few better ones lined up. And anytime you see a shift in how I show things, like a digital drawing, a hand drawing, and whiteboard drawings, that's because I keep changing my mind how I want to present them. That also probably reflects the era in which I return to this theory. So, what happens when we introduce a second mass? If we have two masses, then space-time will stretch from both. Both of these bodies will be independently influencing the space around them, creating a higher space-time density. If these masses are by themselves, then the field will be even on all sides for that mass. Blue for the larger mass, red for the smaller mass. If both these masses overlap, then the resulting gravitational field will warp around both, combining the densities of both to produce a new shape, which is what we expect with gravity. It's accumulative. Having more than one body within a system changes the entire dynamics of gravitational density. Thinking about it logically, one might assume that my theory would push these masses away, not draw them together, but you might be surprised at what happens. The smaller mass will pretend this is a sun-planet system, even though it looks much more like a binary star system. If it was better scaled, the second mass would be much, much smaller if it was a planet. But it's easier to describe this way and keep things visual and less confusing, okay? The planet is now caught in the sun's sphere of influence. The density area around the planet has significantly stretched from what it would be like if the smaller mass was by itself. But everything isn't completely dominated by the larger mass. The planet still has its own region, like an island within a larger system. The larger the planet is, the larger that island would be, and the smaller the planet is, the smaller that island. Returning to the graph images, we no longer have a nice clean bell curve for the stretched space. It is unbalanced. The densities on either side of both masses will no longer be equal, and this will affect the system. The new curve also shows us two things. It shows the smaller shift of the center of mass. Both bodies will be drawn to this new point. And the second is the small dip between both bodies near the smaller mass. This is the spot where the gravitational pressure between the two masses is equal. Anything sitting here would feel equal pull towards both masses and therefore wouldn't be drawn to either. This is called the first Lagrange point. Now here's the interesting thing. In three-dimensional space, anything floating around will be subject to both masses. Even when that object is well in the sphere of influence of one mass, the pull from the other will still be felt. No matter where they are, the faintest of interactions between both masses will still exist. Except, and this is so important, in direct line between both bodies. On a one-dimensional line, the influence is determined by which side of the Lagrange point the body sits. So here's a picture for both bodies and the resulting gravitational density felt by them. The purple fill underneath the curved line is showing which side of the system the bodies will be drawn to if they resided in that space. So another interesting consequence of this quirk is that both bodies are now cut off from part of their normal gravitational pressure on one side. What once was even and keeping everything firmly in the middle now has a lower gravitational density in between the two systems. This results in both bodies experiencing an uneven pressure that draws them towards each other, just like in Newtonian gravity. I won't add it here, but my limited math skills has let me derive a relationship between all these bodies. It can be seen on my website. Not that's worth exploring, but here is the end product. We can now apply the direction of pressure shown with the little arrows below. As you can see, the combined pressure on the left side of M1, the blue and red pressure lines, are now much greater than the pressure experiences on the right side, the green line. Remember, we only count the pressure from the Lagrange point to the mass. We can also see that gravitational pressure on the inside, the green line, of the smaller mass is much smaller again compared to the force pushing from the other side. So that would result in a much more pressure on the outside, exerting a greater force against the smaller mass compared to the larger. The further away the masses are, the less pressure experienced by either of them from the other side. This effect only applies when the two bodies are directly aligned. If we look from a different angle, the combined densities still apply, but there is no cancelling effect. Outside the direct line of sight, the density is a combined experience from both bodies, and any object would feel gravitational forces drawn to both. Okay, so for example, we automatically assume these bodies are orbiting, like two suns or one sun and one planet. But if the bodies aren't orbiting, just sitting in space, they would fall towards each other. The smaller body would move at a greater rate as it has a much lower inner pressure to counter the combined outer pressure. The larger mass is also still unbalanced, with the inner pressure from the Lagrange point to the mass still being smaller than the combined outer pressure. It might have less of an imbalance than the smaller mass, but it is still imbalanced. So the outer pressure wins as well, pushing it towards the smaller object. The difference in balance means the smaller mass is being pushed inwards at a greater rate than the larger one. Throwing a ball. Okay, so we've seen how mass can work on a large astronomical scale, but how does that look on Earth with small objects? Just like the planet-sun example, the gravitational density warps around all mass, not just massive bodies like planets and stars, but all matter, from the largest black hole to the tiniest dust mote, everything. And when you have two or more masses within reach, then they will be drawn to each other, just like our star-planet example. And this applies to everything. The only difference is that unlike what we explored earlier, the primary mass is so dominant that we can effectively ignore the contribution of the smaller mass altogether. This ridiculous, overly exaggerated image shows a nondescript stick figure dropping a ball. Said ball falls to the Earth for the exact same reason why the two celestial bodies are drawn to each other, because the line of sight between the two bodies cancels out the effect of gravitational pressure beyond the Lagrange neutral point between the two masses. If we apply our gravitational field distortion to the ball and the planet and rotate our cartoonishly small world around, then we get our familiar picture, ignoring the skewered hand-drawn wonkiness that is. And just like before, their distortions are accumulative. The difference is, when we picture this on proper scales, the ball is so small and the planet so big that the ball's contribution to the gravitational field's distortion barely makes a difference. And the point where the two gravitational pressures are equal is so close to the center of the ball that it might as well be the center, so we can ignore the small body's mass. The most important information in this scenario is that the line of sight still exists, and as such, we still have both bodies drawn to each other. You might struggle to imagine this, as I did initially. It seems that the cancelling out pressure between the two objects will cause the larger mass to hurtle towards the ball at a pace as dramatic as the ball falling to the planet. But there's something else to account for. The mass area of the planet is so huge that the gravitational pressure lines are almost parallel to the ball's line of sight. That gravitational pressure outside the ball's influence is still bearing down on the planet without interruption. The small gravitational blip that is caused by such a tiny sphere of influence from the ball seems insignificant from the point of view of the planet, and that's the important factor, the sphere of influence of the smaller mass. This also applies to our larger solar system bodies too. Though the sphere of influence of the smaller planet body is considerably large, it's still dwarfed by the sun it orbits, and those power lines still exist around it, drawing enough pressure outside the line of sight down on the sun.